So what are we doing? We're so from last week we got two formulas, right? We have the disk method, which was basically the volume is given by the formula pi integral from a to b f of x squared dx, or pi integral from c to d f of y squared dy, right? And this was rotation around the x-axis, and this was rotation around the y-axis, right? That's what we kind of agreed on. We also had a formula for the area, for the volume when the cross section is bounded. So it came out to be something like the outer radius squared minus the inner radius squared dx or dy, whatever you do. So those are the disk or the washer method, depending what your slices look like. It's all the same thing. The different technique was the cylindrical shell method. So there the formulas were 2 pi and integral from a to b x f of x dx. So this was rotation around the y-axis. So basically you just have to decide which integral is easier to do, dx or dy. Okay? And then you'll decide on the method. Or, you know, the similar thing. Maybe I should say g of y, not f of y. Different function. And this was rotation around the x-axis. Let's do this also. Okay, fun stuff. That's fun. You'll reflect back on these days with nostalgia at some point. So I just want to do a few examples. We're just going to set them up, not evaluate. I assume your proficiency in integration. So set up the following. So the region is bounded by y equals 1 over x equals 1, x equals 3, and y equals 0. So this is the region. So rotate around the x. So basically we just have to decide which way is going to be easier, the dx way or dy way. And that will tell you which method to use. So which way is easier? Dx. So then we're just going to do the disk, right? Because the picture is going to look something like this. You have this guy, and you're just going to rotate it this way. So yeah, this slices are much easier. So then the volume is pi integral dx, so from 1 to 3, 1 over x squared dx. Is that okay? So whatever that equals to, I don't care. I mean, you should be able to do that without any further complications or whatever. Questions on that? You like this stuff? No? Okay. Around the line y equals -2. So again, a quick sketch always helps. It will help us out to just kind of see what we're looking at. So here's the region, and here's the line y equals -2, right? So something like this. There's a hole in the middle. So again, dy or dx. Yeah, so it's the same thing. Now the only difference is it's kind of the area. We just have to figure out the outer and the inner radii, right? So if we just think about this, still integral from 1 to 3, well, what is the big radius here? Right, these are the, what? Yes, it's 1 over x minus -2, so 1 over x plus 2, right? And again, remember how I told you you can always think of the axis of rotation as the new x-axis? You just think about this graph with respect to this new x-axis. So it's 1 over x plus 2. It just kind of went up 2 units, right? Or just stick to the idea of, well, how do you find this length is the difference between these two graphs, 1 over x minus -2. Minus this, which is just -2 or 2, but you're going to square it anyway, so that doesn't matter, right? Yeah, so that's 2 squared. So that's 1 over x plus 2 squared minus whatever, 4 dx. Whatever that equals to. What? Oh. Didn't you fix that thing? Did it give you... Yeah, but did it say that yellow thing here or no? Well, maybe just freaking out. It is warm in here. All right, let's do the y-axis. So if we do the y-axis, so it's so it will rotate this way. What were you saying? Yeah, the shell method, because you want to stick to the dx integral, right? Because again, the second you switch to dy integral, you're going to be, you know, it's a little more complex, right? But yeah, so you want to do the shell method here. So this is our little shells or whatever. So how we're going to set that one up? So it's 2 pi dx integral still. So again, what is x going to range from what to what? From 1 to 3. So the radius of each shell is just going to be whatever the x is in this case, right? Times, and the height is the function, which is 1 over x. So it's really coming out nice and pretty, right? It's just 2 pi from 1 to 3 dx. Is that okay? Does that make sense? Yeah. 4 pi. Right, if you compute that integral.
Right, because there's a 1 in there.
Right, so it's basically 2 pi times, you know, the length of the, so it's 2. How about this one? Rotate around y equals x. No, let's not do that yet. Just y equals 3. So we yeah, only it's a little reversed, right? The shape is like that now. Oh. So this is my weird way to show that it's rotating, but yeah, it's very similar to that. So we're probably gonna do dx integral. So we're gonna do the from 1 to 3. So we just have to decide what is our bigger radius and what is our smaller radius. Right, so the 3 squared is our bigger radius, right? This thing is always going to be 3. So it's 3 squared minus, what is the smaller radius? Right, because again, we're looking at the length of this guy, so it's whatever the difference between the horizontal and the curve. So it's 3 minus 1 over x, also squared, dx. Is that okay? Again, whatever that equals to, we should be able to evaluate. But the question's on the setup. We're good? do. Oh, that's wrong. X equals 5 is the next rotation. Like a what? Yeah, like a racetrack. So how are we going to get this one done? Which method, first of all? The shell, right? So let's using the shell method. So the volume is 2 pi So again, our shells are going to look like this. These are the shells. So when you're building each shell, the x will still range from 1 to 3. Do you agree with that? From 1 to 3, and the height of each shell will still be given by 1 over x in that region, right? So it's 1 over x. Well, the only question is, well, what is the radius of each shell? Because that's what we put here. So for any given x, so yeah, so it's the difference between 5 and whatever this x value is, right? Like, for example, when you're at this point, then the radius is, well, from 3 to 5, the radius is 2, right? When you're at this point, the radius of the shell is 4. Well, at any given point, it is whatever the difference from 5 to that x was. So the radius is 5 minus x, like that. Okay? Because again, if we understand where that formula came from, that this x right here represents the radius. So if you just keep that in mind, the radius of each shell, it will help us to figure out the formulas. How's that? Is that good? Moving on. Want to talk about arc length? Okay. Nah, we have to. I mean, I don't have to. You have to. But maybe it will help just a little bit if I talk about it too. I don't know. Right. So actually, we're going to try to figure out the length of a curve, which we haven't done that before. But we can certainly try. I think this is 7.4 already, isn't it? Yeah. So you're going to have a little 7.4 assignment for Friday. I think I already posted that. So we literally want to figure out the exact length of the curve. We want to figure out how long the curve is on some interval. Okay? so this is the plan. So just anything else that we've been doing so far, we're going to start cutting this thing into little pieces. I'm going to try to figure out the length of each piece and then add everything together. Now we have to be a little careful here, because when we actually start cutting, our piece is going to look, like this or like that or whatever. They're still going to have some kind of a slope or whatnot. So we're actually going to try to approximate the length of each piece by a line segment. Okay? That's what we're going to try to do. And so we just have to figure out the length of each line segment and then add them all together and take the limit and so forth. Does the plan make sense? So let's see what we're going to end up with. So if I take 2 points, let's say these 2 points, x sub I and x sub I plus 1, go up there. Well, I'm going to zoom in here eventually, but let's do some labeling. So let's call this some point pi and this point p sub I plus 1. So this is what I'm looking at. I have a curve, but then it's connected by a straight line. Okay, so I'm going to figure out the length of that straight line. So basically, I'm looking at the distance between 2 points, p sub I and p sub I plus 1. That's what I need to figure out. Distance between these 2 points. Is that okay? Plan makes sense? All right, so I have 2 points. I have coordinates of those 2 points, right? They have the coordinates x sub I f of x sub I and x sub I plus 1, f of x sub I plus 1. So I have 2 points in the plan. I want to figure out the distance. So I'm going to use the distance formula, right? So let's see. So that gives me the square root. Change in x squared, x sub I plus 1 minus x sub I squared plus change in y squared. Good stuff. So, again, we've seen these types of derivations a few times already in this semester. There's a very convenient way of relabeling change in x, right? Yeah, delta x. I'm just going to say, well, as of right now, I'm staring at delta x squared plus, sure, but I want to fix, I want to end up with everything in terms of x eventually. But yeah, you can do that, but then I'll have to do some extra reshuffling. But you're right, this is change in y squared. Okay? Now, my claim is that on this interval, between x sub I and x sub I plus 1, I will be able to find a point. Let's call that point x sub I don't know, star. I can find a point. I don't know, I'm getting a little carried away with my subscripts or whatever. By the way, the function should be differentiable and, everything is pretty. It's one of them smooth, pretty curves for now. What? Well, that's the phrase, right? There's a mathematical definition of a smooth curve. But so my claim is that there is such point somewhere on that interval, so that f prime of x sub I with a little star is the same as f of x sub I plus 1 minus f of x of I over x of I plus 1 minus x of I. Is my claim, does my claim has ground to stand on? What am I just using here? The mean value theorem, right? Because I have a continuous, everything's nice and fancy. Basically, all I'm saying is, you know, at this point, the slope of a tangent line is the same as the slope of a secant line. That's what I'm using. So using the MVT here. Very good. MVT. So by some clever manipulations, this is delta x right here, right? I can say that f of x of I plus 1 minus f of x of I is the same as f prime at some other silly point delta x, right? Just manipulating the formula. So basically, I'm going to use this in here, right? Because this is the f of x, you know, so I plus 1 thing. So then if I make that substitution, that distance between those 2 points now is the square root of delta x squared plus f prime of x of I star delta x squared, like that. Is that okay? So I can do some factoring. I can factor delta x squared out and then take it out of the square root. I'll end up with this, the square root of 1 plus f prime of x of I delta x outside the square root. Is that okay? See what I did? I factored out delta squared and then took the square root of it, so it came out clean. Here? Okay. Well, this denominator is the same as delta x. So just multiply both sides by delta x. So you'll get this, which is the numerator equals. So this will be the length of one little piece, right? So I'm going to add them all together. So if I'm going to add them all together, I goes from 1 to n. And if I take the limit as n goes to infinity, I'll get the arc length. I think your book uses the letter S to represent the arc length. Could you, Peter? Yeah? So S for arc length. So this becomes an integral from a to b, square root of 1 plus the derivative squared dx.
Wait, so how do you find the x or f? Wait, the f or the fx sub I star?
Well, it's just some points on that interval.
Right.
That's what the star is. But when you start, you know, doing the shrinking thing, then, you know, it just doesn't matter, just somewhere in there. So it just basically it will turn into that. It's your function, right? Not really. It's just, I mean,
So the x, wait,
I mean, you do need to just say, but
Couldn't you show that 1 plus f prime of x squared square root of is going to be the length of any triangle, like any tangent line?
yeah, you can just say that, I think, because that's the tangent line, right? So the slope is that. So it's Yeah, you can do that because you can just say it's the square root. You can do it this way. It's a change in y. So that's what you were saying earlier, right? Change in y squared plus that, right? Well, you can do some like this. Like that. And then you pull it out, and this is more efficient. But yeah, you can do that.
More official or efficient? Because that was
No, this is more official because, we drop the MBT in there. That always looks good. But yeah, you're right. We can pull out, because that still represents the derivative, right? So this is dy dx squared dx. Right?
Wait, so the final thing is square integral from A to 1 plus
The derivative squared.
squared. Oh, that's squared, not I.
Yeah, that's the squared. So, but yeah, we can rewrite it. We can just say this is the s. So whatever notation you prefer, you can say it's 1 plus dy dx squared dx like that. I mean, you can say it's from c to d, 1 plus dx dy squared dy. Depending on how you look at the function. Is that okay? But anyways, you just need the formula. It's 1 plus the derivative squared on the square root. That's, and again, this is a manipulation of a distance formula. So let's do a few examples. This is a fun one. Find the length. Find the length of the curve y equals x squared over 2 minus ln of x over 4 between 2 and 4. Bless you. Okay? So everything's nice and pretty. I'm not even going to attempt to sketch whatever this thing is. That doesn't matter. It's not as important as with the volumes. But anyway, so we're probably just going to end up doing this. It's going to be an integral from 2 to 4. And then it's a square root of 1 plus whatever the derivative is squared dx. So it's easier if we try to do it in steps, not just mess it all, don't try to do it all at once. Just take the derivative first, see what you get. Add 1 to it, maybe something good happens. Then maybe it's a perfect square, because you kind of want that to happen because of the square root thing. Otherwise, it might get a little difficult to integrate. But anyways, so first, let's just take the derivative. What's the derivative of this function? So yeah, the derivative of that is just x minus 1 over 4x. Is that okay? So then I'll try to compute the radicand, 1 plus whatever this thing is squared. So I want to try to simplify this because the square root will make it hard to deal with. The u sub. You can, because I mean well, no. No, because of the x in the denominator. because your du is going to get all funky and you don't have it on the outside. But sometimes you'll just have to use du. So. But I don't think it works here, right? But anyways, if I expand that, so what is it? So it's x squared minus 1/2 plus 1/16 x squared. Is that okay? So if I combine like terms, negative 1/2 becomes positive 1/2, which means I can factor it back into the same thing, only with a plus. And that's kind of a good thing. Is that okay? I mean, this is just algebra, just factoring. It's kind of, I mean, we're kind of cheating here because we knew that result, so we just got the same thing with a plus. So put a plus in there, right? So then it's going to work very nicely with the square root, because now it's just an integral from 2 to 4, the square root of all of that. But it's already squared, so life is going to be pretty good, right? We don't need to worry the absolute values because of the positive. Well, almost. We get a plus, right? Yeah. But yeah, the antiderivative is back to x squared over 2 plus ln of x over 4 from 2 to 4. At this point, you're going to have. So whatever that is, you're going to need a calculator, right? It's 4 squared over 2 plus ln of 4 over 4 minus 2 squared over 2 minus ln of 2 over 4. So, whatever that is. You can simplify this, right? This is 8 minus 2, right? So that's 6 plus 1/4 ln of 2, right? Well, because ln of 4 minus ln of 2 is ln of 4 over 2, right? But anyways, whatever that is, you can leave that as an answer. You can plug it in a calculator to get what I got is 617. But the big thing about these problems, you will notice very soon, is that you are really going to have to make the radicand into a perfect square. That's what makes it easy. Okay, because that's what we achieved here. When we manipulated a little bit, we got the square like that. So the square root thing resolved itself. Because this is nasty. I mean, we can, if I just randomly toss a problem on the board, it'll get ugly with the square root. Because, to do u sub, you got to need something on the outside. We'll get through chapter 8 first. How's that? What? What, that?
No, the
Top part. I'll just stop. Okay. Let's do another one. Find the length of this little thing. Find the length of this beauty This one you do want to sketch just to see what you're looking at. Um, I mean, even if we don't sketch that, what does this kind of smells like? Circular thing, right? Because of the squares. So you're gonna you're gonna have a thing that's symmetric around the y-axis, symmetric around the x-axis, and probably centered at the origin. How it's gonna be, we don't know, but at least we can, right? You do see the symmetries. So maybe, I mean, if you just think about this, you can think of this problem like that. You have 4 equal parts, right? What do you think the intercepts are going to be? Just by, by quick examination. Can you find the xy intercepts? Yeah, it's just going to be 1, -1, -1, 1, right? So in order to find the length of this whole thing, you can probably just find the length of one thing and times it by 4. You agree with that? So you probably can just do something like this. Your problem is going to come up to be, the 4 times the interval from 0 to 1, whatever, right? What was that thing you guys told me where you just type in the thing and it just tells you everything there is to know? Yeah? Let's see. Like, yeah, that thing.
With calc, can you calculate the surface area over volume?
We'll try that, yeah. We'll need the arc length to do that. But yes, we can now, instead of just looking at the volume of a solid, we can look at the surface area of that shape too. And that's on the agenda. So let's see. Yeah, right there. Oh, that's not fun. Well, anyways, so just take the symmetry so it's like that. Right, so we're going to end up with, yeah, well, I don't know what you call this thing, but, so it's like this, all equal parts. What? Well, it's not a circle.
No. Is the one side, is that like a circle?
Oh, you mean,
Like,
is this part of the circle? No, I don't know. That's a good question. I don't know. We need to try. I mean, are you saying,
like,
I mean, how would you even test that?
I don't know, see the match. Because, I mean, wouldn't it be a circle around, because, right, the radius would be 1.
Probably not 1, but I don't know. Are you saying all this, if I take all these 4 parts, rearrange them, I might build a circle out of that?
Oh, you could probably take the arc length and multiply by 4 and see if it equals to pi r.
Yeah, but it's, no,
Necessarily.
won't necessarily be circle. I mean, we'll probably have to, we'll that's, we can, I need to think about that. It's a good question. But it doesn't matter at this point. You know what I mean? Um, so anyways, so we're going to, so let's just take one chunk, right? Let's take this piece. So in order for me to get the thing for the piece, I need to solve for y. And I'm going to get a bunch of plus or minuses. I'll just take a plus and go from 0 to 1. Okay? So solve for y. So y to the 2/3 equals 1 minus x to the 2/3. So y equals plus or minus 1 minus x to the 2/3 to the 3/2, right? Is that okay? So just take the positive. So the positive is this. So take the one from 0 to 1. So then the surface, not the surface, the arc length of this thing is going to be the integral from 0 to 1 times 4, because we agreed on 4 equal parts. And then it's the square root of 1 plus whatever the derivative of this thing. So I'm just going to write it like this for now. Squared dx. Right? No, actually, this one works out really well, believe it or not. We're trying to find problems that work out well. Because look, if I started taking derivatives, I'll do all of this on the side here. So the y is 1 minus x to the 2/3 to the 3/2. So in order for me to take the derivative of that, what's going to happen? 3/2 comes down, right? Then it's 1 minus x to the 2/3. Right. So then 3/2 turns into 1/2 as an exponent. Is that right? And then times the derivative of the inside, which is what? Which is negative 2/3 x to the negative 1/3. Is that okay? Does that hold water? Yes. So 2/3 and 3/2 look like they're going to cancel. So this is x to the negative 1/3. Yeah, negative times 1 minus x to the, but again, the negative, we're going to square that thing. So negative will go away. Yeah, that's true, but I'm thinking ahead. But yes, you're right. I shouldn't be. So anywho, it's okay. Because I need to square this, right? Because remember, so that was the first part taking the derivative. The second part, I have to go 1 plus the derivative squared. So this is 1 plus negative x to the negative 1/3 times 1 minus x to the 2/3 to the power 1/2, everything squared. It's a product. I'm not doing much of calculus here, by the way, right? This is algebraic pain, but so squaring, it's a product, so I just need to square both things. So negative goes away, power becomes x to the negative 2/3, right? You multiply powers by 2, and then when you square 1/2, what's going to happen to that? It becomes 1, so it's times 1 minus x to the 2/3. Which negative? Well, this negative goes away because I'm squaring it. But the exponent negative, remember, multiply exponent, so that one stays. So then you need to distribute this. So it becomes 1 plus x to the negative 2/3 minus 1, because it's x to the negative 2/3 times x to the positive 2/3. That's 1. You see, guys? Negative 2/3, positive 2/3. So they're just going to become 0, so 1, or whatever. So 1's cancel. So this is x to the negative 2/3. So that's the radicand. That's nice, because that's a perfect square. I can take square root of that. Will give me x to the negative 1/3. Right? So then the length is 4 times the integral from 0 to 1, the square root of x with negative 2/3 dx. Right, so it's 1/2, so it becomes negative 1/3. So this is 4 integral from 0 to 1, x with negative 1/3 dx. Okay, well, that's nice. So integrating this gives me x to the positive 2/3 times 3/2 from 0 to 1. 0 gives me 0, 1 gives me 1, so that's just 4 times 3/2. Looks like 6. What? Isn't it nice how it worked out?
Yeah. This is, it's just not my go-to answer, which was like 6.
Oh. So not quite the circle of radius 1. So maybe that,
It's like a separate circle. It's like 1 pi or something.
yeah, maybe. Um, would it be easy if we did implicit differentiation on that to get dy? So we wouldn't have to mess with the radicals? What do you think? Let's try it on the side. I'm just curious. If we, because we need y prime, right? So if I take the derivative, so it's 2/3 x with negative 1/3 plus 2/3, nah. I'll still have a y in there some way. Y to the negative 1/3 y prime, right? I start solving. Nah. I lost interest in the rest of this. So anyways, fun? What? Well, now with that. The previous one was rather fun. Okay. So, well, let's do a calc 1-ish problem. I mean, it needs some calc 1 recollections here. Length over hanging wire. Then I have some, whatever, the telephone poles and the wire hanging. And so let's say this point right here has the height A, and the way we did this in Calc 1, we just kind of put it on the coordinate axis, and we'll call this point B, and this point negative B, and this point was A. Do you remember that? Did Steve do that? That was one of the applications of hyperbolic functions. That the formula that gives you this curve was y equals a cosh of x over a, something like that. I don't know. Let that be the formula. So we want to find the length of that of the wire. Is that okay? So again, by symmetry, remember the cosh is the even function, just like the cosine was. So I can do the double of the integral from 0 to b, the square root of 1 plus whatever the derivative of that thing is, Why don't you try it? I'll take a little break. So whatever the derivative is. So you need to take the derivative, maybe recall some of wonderful properties of hyperbolic functions. So what's the derivative? What is y prime?
Technically, there's only one side.
What's the derivative of cos? Yeah, so it's a times the hyperbolic sine of x over a, but then times, by the chain rule, the derivative of x over a, which is 1 over a. So a's go away. So it's hyperbolic sine of x over a. So when you actually look at 1 plus y prime squared, so that becomes 1 plus the hyperbolic sine squared, right? Which is base of this formula becomes hyperbolic cosine squared of x over 2. Right? I can just manipulate that formula like that. So we like that because it's just a square under the square root. So then when I need to integrate, so the length is 2 integral from 0 to b. I don't know why it's over 2, it's over 8. So it's a square root of cos square of x over a dx. So this is where we at. So then if I want to integrate that thing, so what's the antiderivative of cos? Yeah, x over a, but I need to do something else. I need an a, right? Evaluated from 0 to b. Now hyperbolic sine of 0 is 0, so we just left with 2a of hyperbolic sine of b over a. So this would be the length of that curve. So given the value of a and b, we can actually compute that. So like in this case, the a is 10 and the b is 25. So it becomes 2 times 10 hyperbolic sine of 25. So I was kind of right for wrong reasons, but it's okay. Of whatever, 5 halves. Right? So if I plug it in a calculator, 5 halves times 20. So those you got? 121. Okay. Is that okay? So yeah, we do have a little time left to talk about the surface areas. Because we can eventually come up with a surface area of a sphere, which is what? What? That's not what I was asking. Okay, well, let's do some geometry review. Want to do surface? I don't know. Surface area of revolution. So what we're talking about now is just, you take a curve, you take a curve and you just rotate the curve. Don't worry about the volume, just look at the surface area of the object. So whatever this thing is, you're just looking at the surface area. Okay? We'll get to that.
Explaining the geometry.
You take the limit as the like.
No, I'm talking about geometry.
Okay,
How do you do this with geometry?
Well, we can talk about this in our math club meetings, but we're okay with what we're trying to accomplish. It's going nowhere. Just stop. Well, first, let's just talk about a cone, a circular cone. Let's say has a radius h, no r, sorry, and the height h. And let's call this side L. So we should first figure out the surface area of this cone. Don't mind the bottom. We don't need the bottom. We just need the surface area. Because again, if you pretend just taking a straight line and rotating the straight line around the x-axis, you'll get that shape. But it's a hollow on that side, so we don't need the area of the base. I mean, the area of the base is trivial anyways. Who cares about the area of the base? We need the it's okay. So let's, because we don't have that much time. So I mean, we can look it up. We can derive that thing. I mean, we need to remember the area of a sector. If this is a sector of a circle, let's say this is theta. Do you remember those formulas? How to figure out the area of a sector? Well, you don't need pi. It's just theta over 2 r squared. Yeah, right. Because I mean, what? I don't want to do any of that. So the volume of this thing is just pi r L. I mean, we can get all dirty with that derivation. The thing here, there's a nice way to represent L using H and R. They'll come in handy, right? Just by the Pythagorean theorem, we'll get that. So the what should we use? Let's just use A. So the area, the surface area of this thing is pi r, the square root of r squared plus h squared. Is that okay? Now, it will come in handy because when we actually be doing the surface area of revolutions, we're actually going to use those circular cone frustums to approximate the actual surface area. Because if you think about this, if I take a curve, and I rotate it, and if I just kind of, cut it in pieces, I'll be looking at these types of shapes. Okay, so I'm going to need to figure out the surface area of which one of those frustums, we call them, right? Last class. And figure out the surface area of each one of those, and then add them together, and the good things will happen. Now, if we try to figure out the surface area of something like this, so we have two radii, we have two sides. How did I label it? Let's call this side L, let's call this side L1, let's call this R1, I'm going to call this R2. Okay? So the surface area then of the actual cone is going to be pi r times the length of the side, which is L1 plus L. And the surface area of the little one, so the big, little, is going to be, this is pi r2. It's going to be pi r1 L1. right? So then the surface area that we want is the difference of the two. So it's pi r2 times L1 plus L minus pi r1 L. Yeah. Is that okay? So we're just going to do some algebra, a little bit of geometry. So distribute pi r2 L1 plus pi r2 L minus pi r1 L like that. Then I want to do some clever factoring. Pi comes out. Yeah. This is L1 here. So I can rewrite this thing as this. So I can group the L1s together. So that becomes R2 minus R1 L1 plus R2 L. Is that okay? I want to do something about this. R2 minus R1. That's going to get messy. I'm going to have to look at similar triangles. Do you see the two similar triangles? The big one and the little one? Do you see those two? So I can set up the following identity. The ratios in the little one, so L1 over R1 is the same as the ratio in the big one, L1 plus L over R2. Let me take it on the side here. It's getting messy. Cross multiply gives you L1 R2 equals R1 L1 plus R1 L. Subtract this over L1 R2 minus L1 R1 equals R1 L. Factor. So this matches, right? So I'm going to replace that. So we're getting this volume. I'm sorry, we're getting the formula for the area. So I'm replacing this with R1 L. Missing something in there. So to make this formula easy to remember, I can make it like that. I can put a little 2 up front and a little 2 on the bottom. Is that okay? Is that legal? Okay. So the volume then becomes 2 pi and basically the average of the radii times L. This is the formula that we're going to use to approximate the volumes. What? No, yeah, you're right, the area. No, I'm still writing the V's. Okay, so I'm going to need this formula. Sorry for the messy derivation. I can just give you that formula, I guess. All right. So now back to the picture. So this is the calculus part of that. So if you have a shape You have a curve and you rotate that curve, you get, whatever you get. So when you start slicing it, basically all I want to do is to figure out the area of one of those thrusters. Okay, that's all I want right now. So according to this formula, if I call this point x sub I and this point x sub I plus 1, then the volume, again, not the volume, the area of this solid, the surface area of the solid that we get here by this formula will be 2 pi. Then the average of the radii, well, what is the radius here? It's f of xi, and this is f of x sub I plus 1. So I need to average those two. Times the length, right? Now the length is this, and when we're going to start integrating, I mean, we already have a nice way to figure out the arc length, right? There's a nice way to manipulate that. No, I mean, I'm just going to say, I mean, again, what's the plan? We're going to make the partitions very, very, small. Now, what do you think the average of the two heights will approach? I mean, as we're making those things smaller and smaller and smaller. Well, not 1. It's just going to be whatever some value of the function, right? I mean, I can, are these two heights going to be much different? So I can just say, as we shrink, as n goes to infinity, I mean, the average of this 2 will basically approach the value of the function at some x, whatever, yeah.
Like if you have, 5.01, getting closer and closer together.
That's what you were going for, okay. So this thing will basically become the value of the function, while this is the length of that segment. So eventually the surface area will become this. Yeah. There's some calculus voodoo in there. I mean, we didn't even have to mess with the what do you call them, with the cones, because all this thing says that, well, we're just looking at the cylinders anyways. The heights are the same, so the cylinder is the height times the circumference times the height. And this is the height, and this is the circumference. Okay? But there's a nice thing about this formula, because this is really, if we just focus on this part, 1 plus f prime of x squared dx, this is the differential of the arc length. So I can actually think of this formula as it's an integral with respect to the arc length. I can replace this whole chunk with ds. What makes it nice is that it's almost going to be irrelevant to whether I want to do dx or dy integral. It's going to make those computations very easy. Well, we'll do that on Wednesday. We're going to do examples of that. But hey, here's the formula. Sorry, got a little messy. Okay. All right. I'll see you on Wednesday.